So, in the earlier content, what we discussed in machine learning was regression problems, and today we will discuss the another class of machine learning problems which we call as classification. So, this is again another important topic to be discussed in the area of machine learning. So, you must have seen this figure earlier also when I was introducing the area of machine learning. I took this as an example where we were trying to find out whether the face which is present on an image is actually a face or it's like something else. So as you can see that these type of bounding box which we are interested in, these algorithms will be used in high-end DSLR cameras where you will see a bounding box across the face. So that bounding box which comes across the face is nothing but you are training a classifier which you have embedded into the DSLR camera. So basically in at the back side of it, this classification problem is running. So here what you can see is I'm trying to distinguish whether the face is there in an image pixel or not. So we are taking images of size, let us say this is 16 cross 16. So I'm taking an image of size 16 cross 16 and I'm moving this box across the image, and you can easily realize that this portion do not include any face. So this type of sample will be present at this part of the location, whereas if the bounding box encloses a face, then it will be on this side of the boundary. So our target for a classification technique is to come up with the decision boundary which actually separates the two classes, that is the face versus the non-face classes. So this is our target, that is to separate the faces with the non-face using this decision boundary. In the earlier case when we were discussing regression, we came up with the line or a surface which can actually predict the value when you pass a test sample to it. This time here this particular problem is different from there because in terms of the prediction, actually here what you are doing is you are actually classifying the two classes, like you want either face or non-face. So the boundary has to be again learned using the optimization strategies which we have discussed earlier, for example gradient descent. So this boundary we have to come up with in case of classification, and the process of finding this boundary is a bit different compared to finding the boundary in case of linear regression or non-linear regression, but the overall concepts that are involved here also will be nearly same as that what we have discussed in case of regression. So let us discuss how we will tackle the problem of classification, where we want to separate the classes, like for example we have to separate face from non-face. So we want to do that. So let us see how we can do that. So here you see what I am doing currently here is like I have a single feature X, and I want to actually, based on this single feature X, I want to predict whether that sample is 1 or whether that sample is 0. So you can see now I have a table of data points where you have X and Y, and in this X and Y I have several values of X, and the only difference between this and the linear regression is that here in Y you have only two values, 0 1 0 0 1 1. So you will find only two values here, that is either 0 or 1, whereas in case of regression setting what happens is, in that case your Y will have multiple values, like it will be a range of values like 0.1 0.7 like this. You must have seen this when you were solving the experimental, in the lab also you must have seen this, that the value of Y in case of linear regression is a continuous variable, and you are trying to find out a straight line which can which can pass through all the data points X effectively, so that you can estimate the value of Y properly. So the only difference between the classification and the regression is that the target variable is discrete here. So it will be 0 1, So right now it is either 0 or 1, because right now we are considering two classes. If we consider multiple classes, then it will be having 0, 1, 2, 3. Depending upon the number of classes, the y will take different values. So note that in classification, the y's will take discrete values depending upon how many classes you have. Whereas in case of regression, y was the continuous variable. So here you consider only, right now I am considering the case where you are detecting a phase or a non-phase. So as you can recall here, what I am doing in case of phase is, I am saying the label attached to it as y equal to 1. Whereas in case of non-phase, I am saying, let us say a label is attached to it which is y equal to 0. So if I attach a label of y equal to 1 to this phase and y equal to 0 to this phase, then this particular classification comes under the category of supervised learning. And we will discuss unsupervised learning later on, but for this particular lecture and the lecture which we have already finished, that is regression and classification, what we are doing is we are attaching the extra information in terms of the label, which is y equal to 1 and y equal to 0. So this extra information is actually helping the machine learning algorithm to learn the decision boundary. So these both algorithms comes under the category of supervised learning. So now when I have attached y equal to 1 to the phase and y equal to 0 to the non-phase, then this means this particular samples which you have over here are basically the phase samples. These are phase samples. So you have right now 4 samples of phase here, and these images, or basically these all x's, are nothing but they are the image patches, and of size 16 cross 16. So they are actually the samples which are non-phase samples. Non-phase samples. So now what we will try to do is we will try to see whether we can use our linear regression concept here or not. Like, can we do this learning through linear regression, which we have already done. So if we try to do that, let us say if I try to learn that, so what you will see is, if you try to fit a line here which is a linear regression line, then you will observe that that line will look like this. So if you see, that line will look like this. So if you fit that line using the linear regression concept, you will say, okay, I will not do anything else. What I will do is, I know linear regression, so let me fit this line over here and see whether I can get the results or not using that line. So I am trying to show you that why linear regression will fail here. So first reason that why linear regression fails here is that your data points are not accurately covered in this straight line. So if you see here, your line is a straight line, and some of the data points are not lying on this line. So we were trying to find out a line which is, covering most of the data points with minimum mean square error. But here you observe that all these data points which are here onto the left and on this data point, they are not lying exactly on the line. So the idea of fitting a linear regression onto this type of data set, where you have labels either as 0 or as 1, the idea of fitting a linear regression line onto this kind of data set with discrete values of 0 and 1 for the labels is not good. So you can see here, your line is actually like this, which is not properly fitting. So now what we do is, if it doesn't do that, so let us do one thing. Let us try to find a decision where we will say that if your line, this is your line, right, x dot theta is the model. If you recall, our model m theta x is nothing but x dot theta, which we are trying to find out. So this x dot theta is nothing but theta 0 plus theta 1x plus theta 2x2 plus theta 3x3. So this is the model which I am writing in compact fashion in the form of matrices. So you can see that this line is nothing but it's x dot theta only. And what we are saying is, let us take this decision where, if your x dot theta is greater than 0.5, then what I will say is y is equal to 1. And if x dot theta is less than 0.5, then what I will say is that y is equal to 0. This is, additional, thing that we have to impose on this line, because this is a linear regression which is not doing our job. So what we are doing is we are trying to impose this additional constraint to handle the discrete values of 0 and 1. So if I say that your x dot theta is greater than 0.5, that means actually you are focusing on this point, these points. So basically, this 0.5 is nothing but it's a horizontal line like this. If you see, it's an horizontal line like this. So all the values of x dot theta which are greater than 0.5 are nothing but these points which are greater than x dot theta greater than 0.5. So these are the values on this line which are greater than 0.5. So if you project this particular intersection onto the horizontal line, onto this horizontal plane, if you project this point onto this horizontal plane, what you find is that after this point all the values which I am taking, I am classifying that as y equal to 1, and for x dot theta less than 0.5, what that means is you are actually focusing on all these points on the line. So all these points on the line you are focusing which are less than 0.5. So what it means is, on projecting on the horizontal axis, what you observe is that all the points which are lying towards the left side of this particular boundary we are taking as y equal to 0. This is what we have come up with the rule here. So what we are saying that if the value is greater than 0.5, we are taking it as y equal to 1, which is this area, and if it is less than 0.5, we are taking it as y equal to 0, which is this area. So once we have this, you can easily see that you are actually correctly classifying your data samples. How it is possible? It is possible because you can see now that all these samples which are over here are classified as y equal to 1, and all these samples which are here are classified as y equal to 0, as you were actually planning to do so. So you know that this is all y equal to 1, so your algorithm also is giving you y equal to 1 here, as you can see from the samples. And how you achieved it? You achieved it by using this particular condition which you have imposed onto the linear regression line, which you have fit to the data first, and then you passed this decision boundary through this non-linear decision which you are taking. So once you fit the linear regression line, then you are passing it through this decision function which you have written over here. So once you do that, you easily see that you are able to classify these samples as 0, and you are able to classify these samples as 1. So in this way you are able to do the classification. But there is a problem here, and the problem is, let us say you have a new sample which is coming over here, which is far away from the original distribution which is available here. So this sample is also a phase sample, but it is a little far away from the original distribution which is over here. So if it is far from the original distribution, this new sample, then you recall that when we were using L2 regression, at that time I told you that if there is an outlier which is far away from the original distribution, the regression line will actually change its figure. So recall that from our earlier lecture when we were discussing about that. So our linear line which we have fit to the data, original one, is the green one. But now because of this new phase image which is far away from this distribution, what happens is the green line changes to the purple line. So you can see now that this green line is not there. Now the purple line is there, which is the new one, and this new one is coming because this particular sample is coming over here. So what happens now is, the threshold was this. So you can see here, this point was our threshold point. The value is 0.5. So earlier our threshold was this point, which is over here. But now because this line is changed from green to purple, what happened? this threshold changed to this point, and it's now at this point. So what you are calling now is that all these samples, let me change color here. So all these samples after this are y is equal to 1, and all these samples after this are y equal to 0. So now what you observe here is that in this particular decision boundary, when your boundary is changed from green to purple, what happens is that this particular sample which is over here, it is regarded as y equal to 0. Earlier this was, we know that this is a face, but your algorithm is saying that it's not a face because it is giving it as a label of y equal to 0, because this is the boundary which is created, and to the left of this boundary we have non-face images, and this is actually a face image, but it is coming as a non-face image. So it is basically creating an error because of this. So this is an error, and the boundary that it has created is this one, and this sample is created as an error. So your algorithm is creating error over here. So that's why this particular way of approaching the classification problem is a problem, because we cannot do a linear regression fit first and then do this rule which is applied over here. We will not do like that. This is the idea and the motivation that why we cannot use linear regression here to fit to this type of data set, because if you fit the linear regression first, then what will happen is, because of this outlier, your line can change, and if your line can change, and then when you apply this decision of 0.5 and less than 0.5, then this type of problem will happen. So that's why we do not go with this approach of fitting the line first and then passing it through this nonlinear decision boundary. So this type of approach is not valid. So any questions here related to what I have explained? Am I audible to all of you? Okay, so this is basically the way you will do it if you only have linear regression in your mind. But now we will see other ways of solving this problem, because you have seen now that if you do a linear regression and then do the non-linear decision boundary, it is not giving us good results because of this problem which I have told you. So now we will go and see how we can solve this problem. So you recall this slide, because when we started out our course on machine learning, I have already introduced this slide at that time. So by now I think you must be aware of all the blocks which are there in this particular pipeline. So basically what is happening here is, now we want to define a model. So what I was trying to say in the before slide, we are now trying to find out the model for the classification. So in the earlier case of the regression, we have already discussed that model, which was m theta xi, which is x dot theta. We have already came up with this model in case of regression, but now in classification we have to find this model and see what kind of model we can come up with in case of classification. And another important thing that I will point out here is that the label y's here are only 0 or 1, or it can be 0, 1, 2, 3, 4, 5 depending upon how many classes are there, but the labels are discrete and they will not be continuous here in case of classification problems. So that has to be actually kept in mind. So once this is done, so let us see how we can go for learning this model M for classification setting. So from the earlier analysis which we have done here, in this analysis, what we have observed few observations, and the observations are that in classification setting, what happens is our y is either 0 or 1. That is first observation which I am telling you from the very beginning, that is y will either be a 0 or 1. However, when you fit a regression model, as it was the case when we were doing this particular thing, if you observe, when we were fitting the regression model, what we observed is that we will get y in continuous range. So if you see, you will get all the points on this regression model. They are continuous, they are not discrete value, and it can go beyond 1 also. As you can see, all these points are going beyond 1, and all these points here are going beyond 0. So this is less than 0 and this is getting greater than 1. So you can see all these points are greater than 1 and less than 0, and they are also continuous. They are not discrete the way we wanted for classification setting. So we want to address these issues. So the first thing is that our model which we are using through regression, that is actually giving us a value which is greater than 1, or it can also be less than 0, as I have shown you in the image before. So we want to address this problem because we know y is either 0 or 1, but your m theta is giving all the ranges from minus some value to plus some value. So there is no bound on that. So the question that comes naturally to us is how to restrict the range of m theta x so that it can be between 0 and 1. That is our main objective, because we want to restrict the range to lie in between 0 and 1. So in order to do that, what we do is that we already know this model which we have obtained through regression. So you already know this. So right now what we are doing in this particular slide is to come up with the model M, that is what model we want for classification. So we are actually searching for that model. So right now you can see this is the model which you have from regression. And now the first approach that we want to do is, if you see here, our objective is to restrict the range between 0 and 1. So our first approach will be to use unit step function. So unit step function is nothing but it's like, you know, its definition is like this. Its definition is that it will be a value of 1 if your t is greater than 0, and it will be 0 if your t is less than 0. So it's very simple function which we call as unit step. That is, it has a value of 1 if t is greater than 0, and its value is 0 if t is less than 0. As simple as that. If you want to see it graphically, it looks like this. So you can see the definition which we have written over here. I am drawing it graphically, so it looks like this. All the values which are less than 0 are 0. All the values which are greater than 0 are 1. So keep this in mind that this is unit step. So now what we want to do is we want to use this unit step onto this x theta so that we can actually restrict the range of the model in between 0 and 1. In between 0 and 1, because we know that it is going less than 0 and greater than 1. We want to restrict that. So if you know that if you multiply this blue curve which is over here, which is a unit step, with the line like this, if you multiply with this, what you will get? You will get this. So this you will get this, because you have actually multiplied the unit step with the unit step with what? You have multiplied that with the regression line. So you will get something like this. Once you have, you know, basically when you multiply that with the unit step, you will get something like this. So we want to see like how we are getting that. So here you can see this is the operation which I am applying on x dot theta. Here you can see I am applying operation of u on x dot theta. So earlier it was ut, now the t is replaced by x dot theta. So here inside it is x dot theta, which is nothing but t. So the function will take as 1 if x dot theta, or what you can say is t is greater than 0, and 0 when t is less than 0, or x dot theta is less than 0. So if you want to see this plot, it looks like this. So here you can see practically speaking, you know, I have not drawn this to the point, but this is actually a shifted version of the unit step. This unit step is not the same unit step which it should be here. because it's a shifted version of the unit step by amount, which is 0.5 here. So it is shifted by that amount, but you can get the idea that if I am actually applying a unit step onto this line, I will get this particular curve like this. So so this is basically this u x dot theta is basically this definition of 1 and 0 when your x dot theta is greater than 0 and x dot theta is less than 0. So right now, if you observe here, I am shifting this by a factor of 0.5 this side. So that's why what I am saying is x dot theta, if it is greater than 0.5, you will get this particular line, which is 1, and if x dot theta is less than 0.5, you will get this particular line, which is at the bottom. So basically this particular curve is nothing but this equation. To be precise, it is this equation, not this equation, which is this one, because here it is 0 here, right? So ideally this you can understand what I am trying to say here. What I am trying to say is I am applying a unit step onto the linear regression, but this, if you forget for a while, then the definition of u x dot theta is nothing but like this. But we have this 0.5 factor which is coming because of this threshold which is over here. So you can see that it is also shifted to the right side. Unit step earlier was here, but now it is shifted to the right side like this. And the definition of this dotted unit step, which is here, this one, is actually nothing but this equation. So what I am trying to show you now is that this equation and this equation, which is given on the top, are actually equivalent. The only difference is with the value of 0.5, and let me show you that. So what happens is, what is x dot theta actually? X dot theta is nothing but it is theta 0 plus theta 1 x1 plus theta 2 x2 plus theta n xn. This we already know, and we know that it is greater than 0.5. So I am just writing this equation here. So once we write like this, what we can do is we can actually bring this 0.5 this side. So if I bring this 0.5 this side, you can write it as theta 0 minus 0.5 plus theta 1 x1 plus theta 2 x2. Everything else will remain same. So now what we can do is we can actually replace this theta 0 minus 0.5, which is also called as the bias. We can actually call this as theta 0 prime. And you can see now, if I replace theta 0 minus 0.5 with theta 0 prime, it never changes the original function which we had started out with. The only difference is that theta 0 is replaced by theta 0 prime, which is nothing but theta 0 minus 0.5. So it hardly matters because you are actually adjusting the bias only by a small amount. So you can see that this equation also is somewhat equivalent to this original equation which is over here. So we can say that this is nothing but it's x dot theta greater than 0. So you can see that though mathematically they are different, but we can bring in this 0.5 to this side to adjust to the value inside and can make this equivalent to this expression which is over here. So that's why mathematically they are different, but we can adjust the bias which is available here inside this theta and can make this function looks like this function which is over here. So this is basically just trying to tell you that how this u operated on x dot theta looks like. So this is what I have here. So any questions if you have, you can ask me in between. Otherwise I will keep on moving and I will not ask you like whether you want to ask questions or not. You can interrupt me in between in case if you have any questions. So here once we have this thing, then what I am writing is 1 comma 0 with x dot theta greater than 0 and x dot theta less than 0. So this is, we are trying to get it from the definition which we have over here. So you can see from here how we adjusted this 0.5 into this equation and we came with this particular expression here. So now the important question is that how to obtain the optimal values of theta in this ux theta. So the important thing is we have come up with this model. So this is the model for classification. So earlier we started out the discussion that what will be the model for classification. So now we have come up with the model for classification, which is given like this. This is our model for classification. So now the important thing is how to obtain the optimal values of theta that you have in this model, which is over here. So if you recall, in case of linear regression, we had m theta x and we were finding out the optimal values of theta for this m theta x. In the similar way, we are targeting the same objective, that is how to find the optimal values of theta in this x dot theta for this model. So this is again m theta x I, but it is for classification, not for regression. So this model will not be used for regression, it is only used for classification. So there are two ways of approaching this idea of getting the optimal value of theta. The first way is to fit the line and then apply unit step. So this I have told you earlier also, it's not a good way of doing it, because I have shown you that when you have an outlier, so this line will actually move towards the outlier and then it will create problems when you threshold it with unit step. So that thing is not a good approach of doing it. The second approach is to write the combined function. So I am writing this as a combined function and then finding the optimal parameters. So what I am trying to tell is you find this combined function and then you obtain the optimal value of theta. In this particular case, fitting the line means you are already obtaining the value of optimal theta here, and then you are applying a unit step, which creates a problem. So now what you are doing, you are actually combining the function, and now you are actually varying the theta here for the combined function. And we will see how can we find the optimal parameters for this strategy. So we will use this strategy, we will not use this one. So this method which we have discussed earlier on page 3 is not a good method, because I told you the outlier thing. The second method will be discussed next. So this is the loss function that we will have for the classification setting. So this loss function is specifically for classification setting. So this loss function is particularly used for classification setting. So in this loss function, can anyone tell me what is the drawback of this? First of all, we have this as a mean square error. So this is the mean square error that we have, and this is the similar thing that we had done for our linear regression also. If you recall, this is replaced by m theta xi in case of linear regression. Same thing we are doing for classification setting, but our model is changed to u of xi theta. So can anyone tell what will be the drawback here? Anyone? So this is basically the classification setting where we have this particular loss function, which is defined like this. The drawback that we have here is the cost function which we have over here. So here what you observe is, if you plot this particular cost function which is given over here, so it looks like this. So the problem here is that most of the areas where you have this plot of this cost function, it's mostly flat over here. So you can see this is all flat, and the problem is, if you initialize your point on this particular point, then what you will observe is that because it's a flat curve, so your point will not move at all. So it's not moving at all, it's completely flat. Similarly here also, because it's completely flat, it will not move at all onto this horizontal curve. The gradient descent will find difficulty in moving on these flat curves. However, we have some techniques which actually are helpful in tackling this situation where you have flat curves, which we call as normalized gradient descent. So this is again another variant of gradient descent. So basically we use this one for tackling a situation where you have horizontal curves, horizontal portions in which you want to actually accelerate the gradients, and normalized gradient descent actually helps us in doing that. I am not going into the details of that. If you want, you can check yourself. So this is basically the area of optimization which actually tackles with this type of situation. And again, another important point that we want to look over here is that there is a highly discontinuity in this area. So you can see this is a curve, and then you have another curve which is over here. So these points are highly discontinuous, and there is no there is nothing in between the two surfaces. So it's highly discontinuous. So because of this discontinuity thing, the differentiability will create a problem. So functions will not be differentiable on these discontinuous portions. So because of that, and this discontinuity is coming because what you are trying to do is you are actually using a unit step which you are operating on this x dot theta. So unit step is you define like this, and you all know that this particular point, at this particular point the function is not differentiable at all. So because of this discontinuity, actually this is actually reflected over here. So you can see this particular thing is creating a problem here. We can see so many discontinuities are coming. So your gradient descent will not be working over here because of the discontinuity problem. So the another way of solving this problem is through the smoother approximation to avoid the derivative issue. So we know that this is not differentiable at this point. So what we do is we try to find out the smoother version of it, and the smoother version of it can be like this. So if you want to approximate with the smoother function, this is a smoother function compared to the green one which is abrupt. So a smoother function is actually differentiable also. So please note, this particular discussion which I am doing is for group 4, so they have to write it down. So this is for group 4 actually. So they have to submit this assignment by next week. So this is for group 4. So here we have, this is a smoother operation. So we are smoothing out the green one which is highly discontinuous. So what we are trying to do is we are trying to approximate through a smoother curve, and this is the curve which we will try to use. This is basically, you can see, a smoother approximation of the step function, and the definition of this is nothing but it's 1 plus e to the power minus x. So if you actually plot this curve which is 1 upon 1 plus e to the power minus x, what will happen is you will get this curve. This is a smoother operation compared to the discrete version which is like this. So here if you see, now what I am doing is I am actually multiplying it with theta x, which is a parameter involved with theta with x. So if I vary this theta, so you can see if I vary theta from theta equal to 1 to 2 equal to 10, you can see how this curve, which is the red one, is becoming close to the actual curve which is a unit step, but it will not become close exactly unit step, but it will become close to it as your theta is increased. So when you do the training part in your gradient descent, you know that you will adjust the values of theta. So that's why I am showing you this plot, because during the gradient descent your theta will change. If your theta changes, then this curve will change automatically to adjust to the data set. So that is why I am showing you this curve, because this curve will keep on changing till you settle down onto the fixed value of theta which actually fits the data properly. So this is the variation of theta and the curve, how it looks like as your theta changes from a very low value to a very high value. So this is showing you that curve. So what I am doing now is, we have this model x dot theta. Now instead of using on this u times x dot theta, which we were doing earlier and we saw the drawback of that, what we are doing is we are actually now operating on the softer version of it. So basically what I am doing now is I am actually replacing this by x dot theta. So if I do x dot theta here, so earlier that value actually will come out onto this side, so it will become 1 plus e to the power minus x dot theta, and I am writing it as s on the subscript to show that it's a smoother model. M theta x dot theta, s is the smoother version. It's a smoother version of the original model where we started out with unit step. So this is the function, smoother function, and it's given by sigma x dot theta. So the plot of this will look like this. So here this is the model m theta x, which is the original regression model, and now what you are doing is you are operating 1 upon 1 plus e to the power minus x dot theta onto the model m theta x, which is nothing but it's x dot theta here. This is the x dot theta model. So once you operate this particular function onto it, what you get is the purple line, which is the smoother operation. So here you can see the differentiability is not a problem, because now you can differentiate it. Earlier it was a step function like this, which was creating a problem, but now you have replaced it with the smoother version, which is differentiable. So we can use our second approximation of the model by not using unit step over here, not using this, but using this. So this is again second classification model. So this is second classification model. Earlier was unit step, which we saw is not good. So we come up with the second classification model, which is given over here. And so this is actually normal. This is actually much better than the original one, because it avoids discontinuity. So now we want to understand the interpretation of this particular model which we have come up with. So this is the second model. Earlier was here you had unit step, but now it is now sigma times x dot theta. So what we are saying here is we are actually representing sigma x as 1 upon 1 plus e to the power minus x. It is also called as sigmoid function. So logistic sigmoid function. So here we have this function which is given over here, which we are also representing as m theta x. So we are trying to find out the interpretation of this results that we will get from sigma x dot theta. So the interpretation will be like, if this model gives you a value of 0.7, let us say, because you know that its range will be lying in between 0 and 1. So as you can see here, the range is between 0 and 1. So in case if it gives you a value of 0.7, then what we interpreted this value as, we interpret this value as the probability of belonging to class 1. We say that the probability of belonging to class 1 is 0.7 or 70%. So what it says is, when you are doing it for the phase versus non-phase problem of classification, and if your model is giving you a value of 0.7, you will always say that 70% of the time this model is giving you an answer of it's a phase, and 30% of the time it will say that it's not a phase. So that is the physical interpretation of the results that you will get from the model in terms of the value it will throw out. So if it's giving you 0.7 means 70%. If it gives you a value of, let us say, 0.3, that it means 30% of the time the model is detecting it as phase. And why I am saying it as phase? Because I am labeling y equal to 1 with the phase. That's why 30% of the time this model will give you answer as phase, and 70% of the time it will not give you answer as phase. So that is the interpretation of the model. The second thing is, we have again now the loss function evaluated in this format. So you can see earlier we had unit step here, but now we have sigma here, and the advantage of this sigma is it is giving you a smoother approximation. It is giving you a smoother approximation, and it's avoiding the discontinuity. That is the advantage of having sigma. So this is basically the advantage. But now what we want to see is, like, is there any drawback of this cost function or not? Yes, there is a drawback of this cost function also, because right now we are using a mean square error cost function, which is this minus this whole square. So this is a mean square error loss function. This is we are using from the very beginning of our course. When we started out with linear regression, we also used here m theta xi minus yi whole square. So we started our cost functions with this, and then we looked for other versions of the cost functions also, which looked like this, which is L1 norm. So we saw these type of cost functions also. But what we observe now is that in classification setting, these type of cost functions will not work. This one, which is the original one from where we used to do it in regression setting. So now we see that how to actually come up with a different cost function for classification setting. So before going there, we want to see what is the disadvantage of this particular cost function, which was not a problem at all when we were discussing our case of linear regression. At linear regression, we were saying that this particular cost function is convex, but the problem is when we use this particular cost function in case of classification setting, what we are doing is we are doing sigma times xi theta now. Earlier this was not there, but because of the incursion of sigma onto this function, which is xi theta, this particular cost function becomes non-convex. So earlier we were saying this as convex every time, but because of this factor multiplied with xi theta, this particular cost function becomes non-convex. So the problem of non-convexity or convexity means, I hope you know that convex functions, we know that it has a one global minima, and a non-convex functions looks like this. So if you have a function which looks like this, you can see you have one global minima, but you will have some local minimas also here like this. So if your algorithms get stuck onto these local minimas, you will get poor results because you have a global minima here. But in case of convex functions, you have one single global minima and you will hit to this minimum value with no problem. So the problem is in case of linear regression, your cost function is this format for this particular cost function. But when you change this model to the classification model which is given over here, what happens is suddenly this function becomes this type of function which is non-convex. So it's a problem for us to actually deal with this type of cost function, because it will give you a non-convex function, and the problem is you can stuck onto these local minimas and it will not give you good results. So it will not go to the global minima. So we have to come up with some another type of loss function. See, we worked in classification for finding out the model. This is our model which we have found out, but now we are turning our attention to finding out a new loss function. Like, what is the new loss function that can help us in solving this problem which is created because of the square function which we are using over here. So let us show this in the diagram also. So this is basically a one-dimensional representation of the loss function which I am showing. But if you want to represent it in 2 dimensions, it can look like this also. And here you can see if your algorithm is somewhere here at this point, you will see that it will stuck to this local minima. So this is the local minima here, and the global minima is at this point. The problem is because you have multiple such local minimas, it might happen that your algorithm will stuck, like for example, if it is here, it will stuck to this point. So it will not actually go to this point. It will stuck to this point itself. So these are the problems which are created because of non-convex functions. So we want to find out a new loss function which can actually be convex, and using this model as the model for the classification setting. So now this is our target, that is to find out a new loss function which can actually be a convex function. So before going there, what we observe from this loss function, we observe 2 important things. The first important thing is that this function is a non-convex function in case of classification setting, and the reason for that is this sigma is creating a problem. So this sigma is actually creating a problem. It is not a good function. So the second important thing is regarding this value of y. So basically in case of linear regression, you can observe that yi was taking any arbitrary values, but right now here your yi is taking a value 0 and 1. So basically this cost function is valid for all the values of yi. So if your yi are changing from any amount to any amount, this is valid. So we want to actually find out the cost function which handles only discrete values of yi, so either 0 or 1. So we want to handle these type of situations where your yi handles discrete values. Here it is actually available for all the values of yi. So yi can, if you if you plug in any value of yi, it will give you the results. But we want to find out a cost function which is convex in case of classification, as well as it is only handling 0 and 1, nothing else. So we want to design a cost function which actually fulfills two targets. One is handling only 0 or 1 situation of yi, and second, it should be convex and it should not be non-convex. So to address that, we have this as the new loss function. This is the new loss function that we have, and so this is the function that we will use for our classification setting. So if you have any questions related to what I have discussed till now, you can ask. Otherwise, we will start from this section later on. So this is in particularly the new loss function which we have come up with in case of classification setting, and this is the new model which you have for m alpha theta in case of classification. Any questions here related to what I have discussed?